right, so I just want to make a quick video going over some WebWork stuff. And I might as well also mention the written practice. So let's take a quick peek at that. And then I'll do a plug for the next video that's going to come out. So the written practice, which is due on the 24th. Something to expect in this class are these types of questions that we see in 1A and 1B. So a letter in a mathematical expression represents a variable. Is this always true, sometimes true, or never true? And anyway, I'll be sure to do examples of this in the next video where I talk about functions, variables, parameters, and all those things, which is exactly what this written practice is going over. It's functions, variables, and parameters. So if this all seems weird, watch the next video. This one is directed towards WebWork. So let me see, let's go back. All right, so let's go to WebWork. And oh, I already logged on. But as a reminder, when you're prompted to log on, your username should be your EID with all lowercase letters. So mine is AHCAINE. And your password should be your student ID number. Once you get in here, you can go to user settings and you can change that, but that's the initial logon. Okay, so this first WebWork is really just to get us used to WebWork. So there's a few problems I'm going to go through as demonstrations. I believe, well, all right, I'm going a little bit off script, so let me just see if WebWork likes this. It doesn't. Okay, so although on this first WebWork, the first couple problems want us to evaluate expressions such as this, the real power of WebWork happens when you stop evaluating expressions. So eventually you can just enter stuff like this in WebWork and it'll do it for you. So, okay, WebWork doesn't like when I tell it how to compute the number, it just wants me to give it the number. So let's see, what is 2 times 16 is 32, times 3 is 96. So now let's see if it likes it. And it does. So, okay, great. Basically, this is what the first few questions are. So we just need to evaluate these things. Now we get to question 3. And again, it's rare, but I suppose evaluate is a good buzzword or trigger word to know when you have to actually simplify. So as tempting as it might be to tell WebWork, hey, take the square root of, and then inside the square root, let's see, x2 is 7 minus, and then x1 is -5. So let's make that +5. And that's squared plus, and then y2 is 3 minus -2 is +2. And we want to square that. And if I submit it, it won't like it. It says, hey, what are all these things? I'm just expecting a number. So if you're ever getting error codes in WebWork, they're trying to be helpful. They're trying to tell you what's going wrong. And this is saying, I'm not expecting an addition sign, which is kind of WebWork hinting at, you need to give me a number. So, okay, let's give WebWork a number. How about 13? So let's go over here and let's enter 13. And everything's good. All right. But this is the minority of cases that we're going to have to deal with entering numbers in WebWork. So what's the majority stuff going to look like? Oh, right. I should also mention rules of exponents. I did not plan on making a video on. So just really quickly, let's go ahead and talk about rules of exponents while we're here. There we go. Oh, all right. So first off, no matter what number you have, if you raise it to the 0, you get 1. And I believe an expression like 0 to 0 might be undefined. I would honestly have to Google that. It rarely comes up. So we'll just say, just to be safe, if x is not 0, then if you raise it to the 0 power, you get 1. And that might seem a little weird at first, but if you think about it for a while, you realize that's what it has to be, because, for example, hopefully many of us think of raising something to a power, at least an integer power, as repeated multiplication, which is kind of nice. Let's divide both of these sides by 2. And if I do that, well, then I'm left with 2 times 2, which is the same as 2 times. And this power up here, I could compute as 3 minus 1. It's this 3 and this invisible 1 here, and I subtract them. But, you know, I get 2 squared. Okay, let's go ahead and divide it by 2 again, which really, okay, if I want to preserve equality, so let me also just mention, this is the type of work that I might see from a student, and you may or may not lose points because it is wrong. It's just a matter of how nitpicky we have to be on the rubric. So if this is scratch work, maybe it's fine. But as written, this equality here and this equality here are not true because the left-hand side is 4 divided by 2, which is just 2, whereas this next thing is 8 divided by 2, which is 4. So I was writing down equalities as I was thinking, just kind of like in this flow state, which is great for scratch work, but it's not true to hand in. And so if I want to correct it, I really, since I divided that by 2, I have to divide everything by 2, and now the equalities are all true. And I end up getting 2. Okay, and I should have given myself more room. And so with the power of technology, we can now do that. All right. So 2 squared over 2, well, that's just 2. Let's go ahead and divide by 2 again, which means I have to divide everything by 2, everything by 2, divide by 2, divide by 2. And so I'm going to get 1. And, you know, I should have written this as 2 to the 1. And I should have, just like going from here to here, when I had 2 cubed over 2, and I said, well, hey, that's actually an invisible 1 there. So we should write this as 2 to the 3 minus 1. Well, if I have 2 squared over 2, there's an invisible 1 here, and I can write this as 2 to the 2 minus 1, which is really just 2 to the 1, or just 2. And finally, if I have a 2 to the 1 over 2, well, that's 2 to the 1 minus 1, because there's an invisible 1 there, and so I do top minus bottom. And well, wait a second, 2 to the 1 minus 1, that's 2 to the 0. And if you realize that anything to the 0 has to be 1 because you just kind of have whatever's on top and whatever's on bottom are going to cancel out. And that's what it means to have something to the 0. You could really think of like 2 cubed, instead of just thinking of it as 2 times 2 times 2. If you want to make everything be consistent, you want to think of it as 1 times 2 times 2 times 2 times 2. And in general, 2 to the n is 1 times 2 times 2 times 1 times 2, where there are n many 2s. So if n is 0, there's no 2s, and you just get 1. And there's nothing special about 2. I could have had like 14 to the n is 1 times 14 times 14 times 14 times 14 times 14. Here, this happens n times, and if n is 0, all you get is 1. Okay, and if we continue to play this game, you'll start to realize that, wait a second, if I have like 1 over x to some number, that's the same as x to negative that number. And that is why when, well, okay, it's not why, it's all this starts to become kind of circular, because it's just, if you start anywhere, you can derive the other conditions by just kind of playing around enough. So the way I figured out that this was 2 squared was by taking the exponent on top and subtracting the exponent on bottom. But what I'm really doing is I'm rewriting my expression as 2 cubed, that's the thing on top, that stays the way it is, times 2 to the negative 1. So let's get there in steps. I have 2 cubed times 1/2, and then I come over here. So here's 1, here's 2. So division is a lie, division is a lie, division is a lie. It's just shorthand notation for a multiplication with a fraction, okay? And in fact, if you remember this fact, then this whole like, when do you flip and multiply? It's just a result of knowing that, look, on bottom here, this was just a b, but if I write it as a multiplication, it becomes a 1 over b. So I flipped and multiplied. So similarly here, I have a over b times, and now I have to do 1 over the denominator, but that's going to be d over c, so that's a flip and multiply. But anyway, division is a lie. It's always just multiplication by the reciprocal. And that can be useful at times. So, all right, here we are. But then there's just rules of exponents where you can derive them yourself, and you realize that, wait a second, this 1/2 I can write as 2 to the minus 1, and then you can write it like this, and you get this. You can start anywhere you want and end up anywhere you want with this little playground of exponents, so to speak. Anyway, this rule right here is what that WebWork question is testing. So let's hop back to WebWork now. Ranted enough. All right, back to WebWork. So for my problem, the exponent that works is -8. And there it is, boom. All right, let's go to something a little bit more interesting. Let's go to problem 9. Oh, my cough to be gone. Okay. So function composition. Again, I'm going to make a whole other video about functions, variables, parameters, and we'll talk about function composition and things like that. But let me just emphasize the power of WebWork. Okay, so I kind of despise, although I understand why we do it, but I kind of despise that standard notation writes like f of x equals 2x plus 3. And instead, I kind of wish it just said, oh, is there a way we could do iPad and this? No, not really. Okay, sorry, we're gonna have to see my face again while I switch back to the iPad. And I'll just pull up WebWork on my iPad to make it a little bit nicer. Great. Let's get all this. And here. Want to go to WebWork? Are you saved? You might be saved. All right. Sorry you all have to watch this. You can just jump forward when I finally post it, but I'm not going to recut this. So here we go. Great. There we go. Maybe we're looking at number 9. All right. So 2x plus 3 and 4x minus 7. Let's go back to good notes. 2 plus 3 and 4 minus 7. Okay. This is kind of the notation that I think of functions as, where I don't specify what the input is. You can plug in whatever you want here, and that's your input. And whatever it is, you had better put it wherever other places these empty parentheses appear. So if I had to compute f of g of x, well, that's f of and the thing that I'm plugging in there is g of x. So let's see, f of is 2 plus 3. So that's 2 times g of x. Okay, and well, g of x, that's 4x minus 7. So this is 2 times 4x minus 7 plus 3. And we could simplify that, but we don't need to. So this is what I want to demonstrate with WebWork. All right. We have 2 times 4x minus 7 plus 3. Oh, I just hit next problem. Dang, try again. 2 times 4x minus 7 plus 3. And let's hit submit this time. There we go, that's correct. So my personal preference on how to use WebWork is to let the computer do the simplification for me. If I try and simplify this expression by hand, I might make a mistake, right? Maybe I'm thinking, okay, I get that 8x and I nail it, and then for whatever reason, I happen to think this was minus 12 plus 3, and then I get it wrong, and I'm just so frustrated that WebWork doesn't like my answer. Just let WebWork do the algebra for you. That way you don't have to worry about mistakes, okay? All right, let me do one more example. So further down on that same problem, they have some new functions. Big F of is squared plus 1, and big G of is plus 4. Okay, so what is big F of G of star? Well, G of star is what's being put into F, and what F will do is it will square whatever you put into it, add 1. So what I need to put here is G of star. Okay, so what's G of star? Well, G of star is star plus 4. So this is star plus 4 squared plus 1. And okay, it doesn't actually say star, it says X on the homework. here we are. So let's go ahead and just do that really quick. And again, just let WebWork work its magic. If you want to square something, it's Shift-6, and that'll be the little caret symbol. +1. Let's go ahead and submit that. Boom, there it is. Okay, so I just want to emphasize it's nice to let WebWork do the algebra for you. You just have to tell it what to compute. Let's look at this next problem. Right. Okay, so, oh, sure. All right. So the length of an insect is a function of the temperature during development. The volume of an insect is a function of the length. The mass is a function of the volume. Find the mass as a function of temperature. Okay, so before I talk about that, let's just talk about, this whole problem might seem a little contrived, it might seem a little weird, but we do something like what this problem is asking all the time. So consider if you're driving in a car and you're not going too fast, you're going at 30 miles per hour, okay? And you don't go too far. Maybe you forgot your wallet back at home or something. So you only drive for 5 minutes. Okay, how far did you go? How far did you go? Okay, you all might be able to compute this answer without even realizing what you are doing formally mathematically. So let's do the informal route. You might say, gosh, okay, I drove for 5 minutes, and every hour I drive, I know I'm going to cover 30 miles. So I know that I'm going to cover 30 miles in 1 hour, but I don't drive for an hour. I drive for 5 minutes. Let's see, so there's 60 minutes in an hour. So I guess I drove for 1/12 of an hour. And so if you think about it for a while, you realize, okay, I must cover 1/12 of 30 because I only traveled 1/12 of an hour. So 1/12 of 30 miles. This is the answer here. Okay. That might seem a little weird, but let's kind of make this more formal. Let's mathematize it, okay? So we can figure out distance as a function of hours traveled. It's just 30 times hours. Let me convince you of this. If I drive for 2 hours, I claim that I cover 60 miles. I'm traveling 30 miles per hour. I do that for 2 hours. I'm going to cover 60 miles. And if I drive for 3 hours, well, I'm going to cover 90 miles. And if I drive for 1 hour, I'm going to cover 30. And yeah, like this is the formula, but what it needs as an input is hours. Okay. But I can figure out how many hours have gone by if I know how many minutes have gone by. How does this work? Well, I need 60 minutes to get 1 hour. So however many minutes I have, if I divide that by 60, that will tell me how many hours have gone by. Consider like 45 minutes. If I divide this by 60 minutes, in fact, I would have to use 60 minutes per hour to get the units to work out, but whatever. This is 3/4 of an hour. 45 minutes is 3/4 of an hour. If 120 minutes have gone by, that's 2 hours. And you might say, yeah, that seems right. Yeah, well, if you divide by 60, this will be minutes per hour, you'll get 2 hours. So, okay, I can know how many hours go by if I know how many minutes go by. And I can know how far I drive if I know how many hours go by. Okay, and now I want to know how far I drive based on how many minutes have gone by. And all I need to do is take my minutes and convert it to hours. And that's using this function here. And I take my hours and I convert it to distance. And that's using this function here. And the way we do that mathematically, it's really nice with function composition notation. It would just be the composition of the distance function with the hour function. So what does this look like? My distance function, my distance function takes whatever its input is. So here, it takes its input and it multiplies it by 30. So I have 30 times my input, which is h of m. And h of m, let's see, this is 30 times. Well, that's m over 60. So in fact, I can simplify this and I can write this as m over 2. So the function that tells me how far I've driven based on how many minutes is just the number of minutes divided by 2. And, oh, did I do this? 12 miles. No. Let's see. Is 30 over 12 the same as 5 over 2? It is, right? If I cross multiply, I get 60 equals 60. So we learned a much cleaner way to compute the distance. Here's the old way, where I just kind of thought about it and tried to work it out, and I have 30 divided by 12. That's kind of gross. And the new way is you just take your number of minutes and you divide it by 2. And we figure that out using function composition in mathematics, which is wonderful. So, okay, let's go back to the problem at hand. Nope, that's my email. All right, so we have all of this nastiness going on. And I'm just going to set us up with a hint. I don't want to do the full problem for you. So if we know the temperature, we can compute the length. And if we know the length, we can compute the volume. And if we know the volume, we can compute the mass. And what we want to be able to do is just go from temperature to mass. And so it's going to be multiple function compositions. That's the whole idea. Okay, that is all I want to talk about in this video, just some WebWork tips. I will see you next time. So.